Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about a module Radioactive Waste and its Management from the paper Energy Related Materials. So students, let us see what are we going to learn from this module. From this module, you may get to know about the following. First, the meaning of radioactive waste and nuclear fuel cycle. Second, types of radioactive waste. Third, amount and which is produced and purification of radioactive waste. Lastly, storage and disposal of radioactive waste. Before going into the details of this module, let us start with some introduction about the nuclear or radioactive waste. Nuclear or radioactive waste are the byproduct materials from nuclear reactors, fuel processing plants, medicals and research centers. These materials looks the same way as of the nuclear fuel. However, as nuclear reactions have followed, the contents are not the same anymore. It is important to know about the nuclear fuel cycle for better understanding of radioactive waste. A nuclear fuel cycle consisting of series of industrial procedures to produce electricity from nuclear fuel in nuclear power reactors. All the activities associated to the production of electricity from nuclear reactions are collectively belongs to nuclear fuel cycle. It starts with the mining of radioactive fuel materials and ends with the disposal of nuclear waste. Hence, all the processes related to the production of nuclear energy, such as fuel mining, fuel milling, fuel conversion to its pure form, fuel fabrication, and working of nuclear plants produced certain amount of waste which needs to be managed effectively as per the technical requirements and internationally accepted norms. The introduction about the radioactive waste is already explained. This figure shows the schematic of nuclear fuel cycle. The main objective of radioactive waste management is to handle the radioactive waste in such a manner that it protects human health and the environment at the present and in the future without imposing undue afflictions on coming generations. There are different types of radioactive waste which are generated during each stage of fuel cycle. To fulfill the objective of radioactive waste management, it is essential to consider the following factors such as the amount of waste, waste activity, and radiotoxicity during the treatment, conditioning, and disposal operations. Radioactive waste. Radioactive waste is created at all points in the nuclear fuel cycle from uranium mining, fuel enrichment, discharges from the plants to the highly radioactive waste resulting from reprocessing spent fuel and decommissioning contaminated sites. Radioactive waste also contains radioactive fission products. They can be hazardous for thousands of years. They have fission products, if released, can build up in the body and can be fatal. This table summarizes the above or the previously discussed factors of waste generated at different stages of the fuel cycle, including reactor operation and decommissioning. However, the major waste types are recognized as high level waste or HLW and low intermediate level waste LILW with short and long lived nuclides. Now students, let us discuss about the types of radioactive waste. There are various methods used to categorize the radioactive waste. Their selection usually depends upon the amount of produced radioactive waste material. For instance, an operator of nuclear power plant generally categorizes radioactive waste on the basis of originating stream from the plant. However, this categorization of radioactive waste types is difficult to use extensively because the generated streams vary from case to case. Hence, a classification system that ensures qualitative considerations affecting the final disposal of the conditioned waste is desirable. A classification system of these waste categories are discussed in the table, which separates the radioactive waste types on the basis of two key characteristics: thermal hazard and requirement for disposal. There are various types of radioactive waste, such as, first we'll start with very low level waste, denoted as VLLW. Second, low level waste, that is LLW. Third, intermediate level waste, ILW. Fourth, high level waste. Fifth, mining and milling. And lastly, the conversion, enrichment, and fuel fabrication. Types of radioactive waste. The table briefly describes the types of radioactive waste. Now let us discuss each radioactive waste one by one. First, we will start with very low level or VLLW waste. VLLW includes the radioactive materials at a level that is considered rarely harmful to the people or the surrounding environment. It mainly composed of demolished material like concrete, plaster, bricks, metals, valves, piping, etc., which are produced during rehabilitation operations on nuclear industrial sites. Besides this, other industries like food processing, chemical, steel also create VLLW due to the availability of small amount of natural radioactivity in minerals used in manufacturing processes. Hence, these wastes are disposed of with domestic refuse. However, few countries, such as France, are trying to develop facilities to store VLLW. Next is low level waste, LLW. LLW is produced from hospitals and industries that consist of paper, rags, tools, clothings, and filters, etc., which composed of smaller quantities of mostly short-lived radioactive nuclides. These wastes do not require any shielding during their handling and transport. In order to reduce the volume of LLWs, compaction or incineration before disposal is done more often. Next is intermediate level waste or ILW. ILW contains higher quantities of radioactive nuclides, thus required some shielding during handling and transportation. These wastes composed of resin, chemical sludge, and metal fuel cladding and contaminated materials from reactor decommissioning. ILWs make up about 7% of the volume and have 4% of the radioactivity of all radioactive waste. The above three types of waste are not tabulated in the table. Now we will start with low intermediate level waste or LILW. LILW is another type of waste which is characterized by or categorized by low heat generation and is divided into subcategories like long-lived waste, that is LILW, LL, and short-lived waste, that is LILW, SL, depending on the degree of containment needed for long-lived radionuclides and alpha emitters. LILW long-lived needs geological disposal. However, some countries dispose LILW short-lived in surface facilities. The boundary between the long-lived and the short-lived wastes regarding the concentration levels of radioactive waste disposal cannot be quantified in a universal manner, as acceptable concentration levels depends on management options. Though several countries bound the long-lived alpha emitters concentration to 400 becquerel per gram in near surface disposable facilities. Strong norms are made in the need of shielding while normal transport of these waste types, and the guidelines in this regard can be found in the regulations for the safe transport of radioactive material as decided by international atomic energy agencies. Apart from this, a radiation requirement also made for conditioned waste generated from nuclear power plants. As per IAEA regulations, LSM must have an unshielded radiation level less than 10 millisv per hour within the periphery of 3 meters. Consequently, few LILW have to be transported with proper shielding in agreement with the transport regulations. Furthermore, few countries have diverse approaches of categorizing radioactive waste, such as the United States classified radioactive waste in different classes, which are A, B, or C on the basis of nuclides concentration. Next type of waste is high level waste or HLW. HLWs are generally produced from spent nuclear fuel or arises from burning of uranium fuel in a nuclear reactor, comprises of high concentration of short and long-lived radionuclides and needs a high degree of isolation from the environment. The recycling of SNF generates significant amount of heat from radioactive decay, which continues for many decades until and unless the concentration of high energy emitters is not reduced. The heat generation rate is considered of about 2 to 20 kilowatt per meter cube for decay time of around 10 years after discharge of SNF from the reactor. HLWs are extremely radioactive and hot because of decay heat, thus needs cooling and shielding. They account more than 95% of total radioactivity created in electricity production. HLW contains both long-lived and short-lived radioactive nuclides. Here we will be discussing about the amount of radioactive waste produced and its composition. Generally, the amount or the quantity of radioactive waste produced by nuclear plants is very small compared with the other waste produced. Nuclear power generation plants around the globe produces about 200,000 meter cube of LLW and ILW and about 10,000 meter cube of HLW each year. The Organization for Economic Cooperation and Development (OECD) countries produced some 300 million tons of toxic waste, and conditioned radioactive waste amount to only 81,000 meter cube each year. For example, UK itself produced total amount of 4.7 million meter cube radioactive waste, out of which 1 million meter cube has already been disposed. Furthermore, about 94%, that is 4.4 million meter cube of UK's total radioactive waste belongs to LLW category. 5.9% of its radioactive waste falls in ILW category and around 0.1% belongs to HLW category. The volume of HLW is comparatively small, which comprises about 95% of the total inventory of radioactivity. The composition of radioactive waste depends on which fuel was placed into the reactor, operating time of the reactor, and how long the radioactive waste was kept out of the reactor. A typical composition of radioactive waste collected from the nuclear reactor is presented in the table. It is noteworthy that most of the uranium remains in the fuel when it is separated from the reactor as waste, even though its enrichment has fallen significantly. This uranium can further be utilized in advanced fast reactors as nuclear fuel for valuable energy sources. On the other hand, the minor actinides, which contain neptunium, americium, and curium are very long-lived nuclides could result in serious concern if stored for more than 100,000 years. Providentially, these nuclides are fissionable, hence can be utilized in fast reactors as fuel. In this slide, students, we will be discussing about the waste treatment technologies and conditioning technologies. So let us start with the waste treatment technologies. Solid waste treatment technologies are primarily meant to reduce the waste volume in order to simplify temporary storage and final processing of disposal. The most obvious solid waste management technologies as follows. First, decontamination or the clearance of bulk material and the processing of small volumes. Second, shredding and cutting of bulk pieces. To embedding bulk pieces into inert matrix. Third, compaction to reduce temporary storage. And lastly, incineration and super compaction. On the other hand, liquid waste management or treatment technologies meant to reduce bulk amount of liquid waste either via evaporation or via separation of radionuclides from raw liquid waste by means of filtration and sorption techniques. The evaporation resulting from liquid concentrates of higher activity, whereas filtration and sorption of radionuclide results smaller volume of absorbents. Both usually belongs to intermediate level waste category. The liquid waste treatment technology results following categories of treated waste. Firstly, dry solid waste, dispersed solid, small equipments and pieces of various materials. Second, wet solid waste, spent filtration materials and ion exchange resin. And lastly, the liquid waste, the aqueous concentrates, organic liquids or oil, etc. Now students, let us come over to the conditioning technologies. The radioactive waste after treatment must be further conditioned for final disposal. The main aim of conditioning is to provide appropriate isolation of radioactive waste from the environment inside waste packages. The solid or the package mainly consists of the processed waste with or without the chemical binding of the radionuclides and a container that provides extra isolation of the conditioned waste from the environment. Nowadays, sets of established waste conditioning technologies are commercially available and extensive active experience has been accumulated. However, the development of conditioning technologies with significant improvement is under progress. In this slide, we will be discussing about two types of conditioning technologies. First is solid waste conditioning technology. Second is liquid waste conditioning technology. Let us start with solid waste conditioning technology. These technologies are being selected on the basis of particular waste properties and waste form. For example, for dry solid waste, including textile material, paper, small tools, air filters, maintenance waste, metals, insulation, electrical cables, as well as fuel cladding, hulls from fuel reprocessing, etc. The following technologies, such as compaction, combustion, embedding of non-compactable and non-combustible into inert matrix, such as cement, polymers, metal recycling, packing into high integrity container, encapsulation in inert matrix, etc. The high temperature technologies, including steam reforming, and verification, produces ceramic like waste with excellent chemical stability. However, these methods are still have limited industrial applications. Next is liquid waste conditioning technologies. Liquid waste types are mainly including aqueous radioactive concentrates that sometimes comprises of crystallized salts and sludge, which produced in storage tanks. Organic liquid waste generally produced in smaller volume. Organic solvents resulted from fuel recycling might raise some serious issues. However, organic waste produced in the end with small volumes. Cementation and bituminization are well developed methods for liquid waste conditioning. Nowadays, high temperature technologies, including verification, plasma torch, etc., are being investigated and tested. In cementation, the liquid waste is generally mixed with cement and special additives, resulting in the binding of radioactive components and increases the quality of the resulted waste. On the basis of chemical composition of the waste, radioactive elements are either encapsulated or chemically bonded into the cement matrix. On the other hand, bituminization is low temperature technology which is based on encapsulation of crystallized waste radioactive elements into a bitumen matrix. Commonly, the liquid waste is introduced into the heated bitumen vapor through thin film rotor evaporator, where water gets evaporated and a uniform mixture of crystalline salts with bitumen is prepared, which is then transferred into the containers. A less common technology including the mixing of evaporates and bitumen in extruder. Salinity of the waste ultimately decides the volume reduction factors and expressed as the contents of salts in the final product. Here the leaching properties of radioactive waste are generally better than the cemented waste. The main issues with this technology are biodegradation of the bitumen component of the waste form and the risk of fire while expansion connected with the oxidants in the waste. However, both the issues can be resolved by using secondary containers where several drums with bitumenized waste are placed in the repository and free space is occupied by cement plaster. Radioactive waste disposal. Improved reprocessing technologies could easily separate the disturbing radioactive elements such as long-lived actinides into chemically pure form, which avails an opportunity to place them in a specially adapted matrix showing better performance as compared to the present methods. prior final disposal, the bundles of spent nuclear fuels is encapsulated within disposal canisters after cooling for at least 20 to 30 years for temporary storage. However, no encapsulation plant is under operation at present, while normal operation of an encapsulated plant, radioactive waste is created only when active elements are generated from the structures of the bundles. This may occur in a rainy storage pond. Most of the reactive material or crude generated in the hot cell is intended to be collected and keep within the disposal containers. SNF is stored in various systems such as water pools, dry air cooling facilities, and containers. The reprocessed vitrified HLW is stored in dry facilities or containers. SNF is usually collected from nuclear reactors into water pools, which provide excellent heat transfer essential for cooling. These water pools are combined with reactor building, where SNF management is a part of the nuclear power plant operation. Water pool storage of SNF is a common technology located outside the reactor building that requires active processing methods to ensure appropriate performance and continuous care to preserve water purity. New design such as passing cooling has been considered recently. The SNF can be transferred from water pool to a naturally cooled dry storage after a few years of initial cooling. The minimum time period of initial cooling in the pools mainly depend to the burn-up and irradiation history. Generally, 20 to 50 years are required for the storage. There are several common facilities available commercially for dry storage of SNF, and they differ from each other in terms of construction materials, size, modularity, configuration, and layout of the storage containers. Dry storage of SNF in larger barrels is recognized as a flexible option with the benefit of transportability in the case of future need. The dry storage facilities for SNF or HLW are same, however, they are different in geometry. So, students, let us summarize what we have learnt from this module. In this final lecture, we introduced the radioactive waste, its types, and treatment or management technologies. We also discussed about other forms of radioactive waste. Finally, we covered the storage of spent nuclear fuel. Thank you.